For group homework assignment number 2, I'm doing problem number 1. And so for this question, it is asking us to calculate the isoelectric point and the average charge on arginine when the pH is equal to 9.2. So first off, let's calculate the isoelectric point. So what we're going to first do is get the charges of each molecule. So this first molecule has 2 pluses, so it's going to be +2. This has 2 pluses and a -1, so it'll be +1. This has a plus and a minus, so it'll be 0. And this has a minus sign, so it'll be -1. Now that we've done that, we can see that this 0 point is what we're looking for, because at isoelectric point, when isoelectric point is equal to pH, it'll be 0. So we want to look at this little section, mainly 2 and 4 right now. So to calculate the actual isoelectric point, we're going to look at the pKa's in between that surround the 0 value, and we're going to take the average of them. So we'll come over to this side, and we'll do 8.99 plus 12.5 divided by 2. So when we calculate that, we get 10.745. 10.745, which is also 10.75. And this is going to be our isoelectric point. Now, we're going to solve for the average charge. So, when we're solving for average charge, there's a lot of different steps that go into this. First, we need to determine the acid and the base. To determine the acid, we're going to look at whichever pK is the closest to the pH, and in this case, it's 8.99. So we're going to look at the 2 molecules that surround that pKa, and it's going to be 2 and 3. The more positive charged molecule is going to be the acid, and then less is going to be the base. Now, we're going to use this formula to find the average charge. pH equals pKa plus log of base over acid. Base and acid. So we know that the pH is 9.2, so we'll plug in 9.2, and we now know that our pK is 8.99 because it's the closest out of all of the other pKs to the actual pH. And then we'll calculate plus log of this ratio. So we'll subtract 8.99 from both sides, and we get 0.21 equals log of the ratio. So then we want to take out the log, so we'll put in a base 10, and that'll cancel that out. And so 10 to the 0.21 power is going to be 1.62 is equal to the ratio, which we're going to finally write out. I just want it to go fast. And since this is a ratio, we want to put this all over 1, right? So now we're going to calculate the average, or we're going to calculate the weighted average to finally get the average charge. So for the weighted average, we're going to compare the base and the acid and its charges. So first we're going to do 1.62, which is a base, and the charge of the base is 0. So we'll multiply that times 0. We'll add it to the acid, which is 1, times the charge of the acid, which is +1, and that's our top. Over the bottom, since we're doing a weighted average, we want to add the total compound. So it's 1.62 plus 1. This is going to give us 1 over 2.62. And then when I plug this 1.1 divided by 2.62 into my calculator, that gives me 0.38, which is going to be our average charge.
This is Drew Dixon solving question 2 on homework 2. We have the equation step where we write down our reaction quotient equation: concentration of C to the power of C, concentration of D to the power of D, concentration of A to the power of A, concentration of B to the power of B, understanding that the top are products and the bottom are reactants. Now we can use the equation given to us to help us input our known variables, put in carbon monoxide and hydrogen in the denominator and methanol in the numerator. Also note that we square hydrogen because it uses 2 moles in the reaction. Once we solve for our quotient, we'll compare it to our constant. In this case, our constant at 14.5 is smaller than our quotient at 28, meaning that the reaction will be product shifted.
So for this problem, we need to find our delta G as well as find the temperature at which the unfolding of the lysozyme would be favorable. So first we'll start with delta G. So we know that delta G equals delta H minus T times delta S. Oh, that looks like an A. Delta S. Okay. So in the problem, we're given delta H, which equals negative 280 kilojoules per mole. Delta S, which is given to us in negative 790 joules per mole, but also can be converted to negative 0.790 kilojoules per mole. T, which is our temperature, is given to us in 25 degrees Celsius. However, we want it in Kelvin. So in order to get Kelvin, we'll just add 273 Kelvin equal to 298 Kelvin. So with this, just plug and chug. So we say delta G equals negative 280 kilojoules per mole minus 298 Kelvin times negative 0.790 kilojoules per mole. And when we plug all that into our calculator, we get delta G is equal to negative 44.58 joules per mole, approximately negative 44.6 joules per mole. So now we want to figure out a temperature at which the unfolding process would be favorable, right? So we have unfolded on the right side and then folded on the left. So at what temperature would this side be favorable? So what we do is we set delta G to 0 and we plug in our delta H and our delta S. So we know our delta H is negative 280 kilojoules per mole. We're looking for our T, and our delta S is negative 0.790 kilojoules per mole. So, work this problem out. We add 280 to both sides. That's 280. We get 280 equals negative T times negative 0.79 kilojoules per mole. And we're going to divide by negative 0.79 kilojoules per mole on both sides. And we get negative 354.45, which equals a negative T. But remember, there's an imaginary 1 with that negative sign. So we're going to divide by negative 1, which will give us 354.45 Kelvin is equal to our temperature at which our protein will unfold. So this means anything above this temperature will be unfavorable. Anything above this temperature will be favorable. Yes.
This is homework 2. It's going to be question number 4. I'm doing parts 1 and 2. So just by looking at this chart, we're going to be dealing with FAD plus 2H plus plus 2 electrons, which will lead to the donor being FADH2. And then the standard reduction potential is going to be negative 0.219. So we're also going to be dealing with the NADH equation as well, which is the NAD plus the H plus positive plus the 2 electrons, which will make the donor NADH, and then the standard reduction potential will be negative 3.15. So according to the chart and according to the problem that we are giving, the highest electrode potential will be the electron acceptor. So in this chart, we have 0.219, negative 0.219, we have negative 0.315. So that will make the FADH the acceptor, FADH the acceptor, and then the NADH the donor. So basically it is based off of the standard reduction potential, depending which one will be the acceptor or which one will be the donor. So then it kind of leads into like question number 2. Write the reaction in the direction that is favorable in thermodynamics. And according to thermodynamics, it is favorable in the anode direction. So it's going to be written as on here, FAD plus H plus NADH, or you could write it as FAD plus NADH plus the H plus, and then it's the equilibrium. You can do NADH plus, or you can do FADH squared or to the second plus the NADH plus.
This is Juliana Boyette solving question 4, part 3 of homework 2. So we need to calculate the standard free energy changes for the reaction in question 4, part 2. So for this equation, or that reaction, we will be using this equation, which N will be number of electrons, F is Faraday's constant, which is 96.5 kilojoules per mole times volts, and then delta E will be taken from this chart up here. So we know that our electron acceptor is FAD, so we will keep negative 0.219, and our electron donor is NADH. So this equation up here will be flipped, and we will also change the sign and use positive 0.315. So our delta E is negative 0.219 plus 0.315 to get 0.096 volts. So when we put that all together, delta G naught prime equals negative 2, and we get the negative 2 from up here. So when you flip this top equation, the 2 electrons will cancel out in our final equation as shown here, but there's still 2 electrons being exchanged, so N will equal 2. Then we'll do times 96.5 kilojoules per mole times volts, and then we will multiply by our delta E, 0.096 volts. Our volts will cancel out, and that will leave us with our final answer, which is negative 18.528 kilojoules per mole.